Hi everyone, I hope you're keeping well and that you followed the first 3 parts of Lecture 2. In this part 4, we will investigate cubic curves and in particular elliptic curves and their link with number theory. Cubic curves in the plane are defined by equation of 2 variables like the one you can see on the screen. Here we are interested in equations with integral coefficients, which means that a, b, c, d, e, f, g, h, I, and j are integers. To ensure to get a curve of degree 3, we must have a, b, c, and d not all 0. Roughly speaking, and for our purposes, an elliptic curve is a particular cubic curve of the form y squared equals x cubed plus ax plus b, where a and b are both integers. We must add the additional condition that the polynomial x cubed plus ax plus b has no repeated roots, which is equivalent to the fact that 4a cubed plus 27b squared is different from 0. It is not very obvious why both of these conditions are equivalent, but do not worry because we will study this in depth in future lectures. Now, before we go through technical details, let me tell you an incredible story about an incredible mathematician. Srinivasa Ramanujan was an outstanding Indian mathematician with an uncommon life story. Unfortunately, Ramanujan was plagued with health problems, and if you do the math here, you would notice that he died at an early age. Our famous mathematician here made groundbreaking contributions to mathematics, and especially to number theory. When he was sick, the British mathematician Godfrey Harold Hardy gave him a visit at the hospital and told him that he took taxi cab number 1729 and that this number seemed dull to him. Hardy was surprised by the negative response of Ramanujan, who told him that actually this is a very interesting number because it is the smallest number expressible as a sum of 2 cubes in 2 different ways. Indeed, 1729 is equal to 1 cubed plus 12 cubed, but is also equal to 9 cubed plus 10 cubed. However, notice that 91 is 3 cubed plus 4 cubed, but is also minus 5 cubed plus 6 cubed. 91 is smaller than 1729 and it is expressible in 2 different ways as a sum of 2 cubes. This does not contradict Ramanujan because he considered only positive integers. In terms of equations, the quest of taxicab numbers n is equivalent to finding the integral solutions of the equation n equals x cubed plus y cubed. And as you can see, this is a cubic equation in 2 variables. Our little anecdote ends here, but if you are interested in the life of Ramanujan, go see the nice movie The Man Who Knew Infinity. We now move on to another famous question which states which integers n can occur as areas of right triangles with rational sides. This problem is known as the congruent number problem. In this video we investigate the case n equals to 5, and our question is now equivalent to finding a right triangle with rational sides and area equal to 5. In what follows, we prove by straight calculations that locating rational points on the elliptic curve y squared equals to x cubed minus 25x give us answers to our problem. This is the graph of our elliptic curve, and notice that it is not the graph of a function. Now before we start, notice that the smallest right triangle with integral size is 3, 4, 5, and that its area is 3 times 4 divided by 2, which is equal to 6. This means that right triangle with integer sides will not answer our problem and that we must look at triangles with rational sides. Now if you take a look at the triangle 7 halves, 12, and 25 halves, we see that this triangle is a right triangle by a simple calculation. It is easy to verify indeed that 7 halves all squared plus 12 squared is equal to 25 halves all squared. And its area is equal to 7 halves times 12 halves, which is equal to 21. This means that a triangle with rational sides can have an integral area. Let us now get back to our main problem, and let me remind you that we would like to find all right triangles with rational sides and area equal to 5. Algebraically, this is equivalent to the fact that a squared plus b squared equals c squared, with a, b, and c rational, and AB is equal to 10. This first condition means that our triangle is a right triangle, and the second condition means that the area is equal to 5. Now if you compute a plus b divided by 2 all squared, one finds a squared plus b squared plus 2ab all divided by 4, which is equal to c divided by 2 all squared plus 5. On the other hand, a minus b divided by 2 all squared is equal to a squared plus b squared minus 2ab all divided by 4, which is actually equal to c divided by 2 all squared minus 5. Now if you set x equals to c divided by 2 all squared, one gets that x minus 5 is equal to a plus b divided by 2 all squared, and x plus 5 is equal to a minus b divided by 2 all squared. Notice here that x minus 5, and x plus 5 are squares of rational numbers. Said in other terms, we're looking for a number x such that x minus 5, and x plus 5 are squares of rational numbers. This means that the number x minus 5 times x plus 5 must be a square of a rational number 2. And this can be written as y squared equals to x cubed minus 25x. Let me go through this again. We showed that if ABC is a right triangle with area equal to 5, then the number x equals c divided by 2 all squared is a rational number on the elliptic curve of equation y squared equals x cubed minus 25x, such that x times x minus 5 times x plus 5 is a square of a rational number. Oops, something is wrong here, and I hope you notice that I made a mistake. Actually, x plus 5 is equal to a plus b over 2 all squared, and here it is x minus 5. Now all we have to do is to locate rational points on this elliptic curve to answer our problem. We will use here the Diophantus-Coord method to locate rational point on our elliptic curve y squared equals x cubed minus 25x. Notice first that we have three trivial points, which are the point A of coordinates 0, 0, the point B of coordinates 5, 0, and another point which is C of coordinates minus 5, 0. Unfortunately, these points will be useless for us because they do not yield any triangles and they lie on the same line. Which means if we apply Diophantus-Coord method, any line passing through two of them will intersect the curve in the remaining point, which is useless for us, of course. Now if we take a closer look to our curve here, we see that the point minus 4, 6 lie on our curve. Now this point is also useless for us because minus 4 is negative and we're looking for x rational positive numbers, but we hope that the Diophantus method will yield another rational point which is positive. Moreover, and unfortunately, notice that any line passing through D and one of the points here do not give us any interesting rational point. However, the tangent line passing through D is an interesting line. I will use here a technique from calculus to determine here the equation of our tangent line, but if you do not know what this is all about, do not worry because I'll do a crash course on it. Let me remind you that the equation of our elliptic curve is y squared equals x cubed minus 25x, and that we're looking for the tangent line passing through the point minus 4, 6. Implicit differentiation yields that 2y, y prime is equal to 3x squared minus 25, which yields that y prime is equal to 3x squared minus 25 all divided by 2y. If you do the math with x equal minus 4 and y equals 6, one finds 23 divided by 12. This means that our tangent line has equation of the form y equals 23 divided by 12x plus a certain number b. After easy computation, one finds that the equation is 23 divided by 12x plus 41 divided by 3. Let me remind you that the tangent line is a line passing through D and the curve twice, which means that this line must intersect our curve in a third rational point. Let me write things down again. We would like to solve the system of equations y squared equals x cubed minus 25x and y equals to 23 divided by 12x plus 41 divided by 3. By substituting the second equation into the first, one first gets that 23 divided by 12, x plus 41 divided by 3, all squared is equal to x cubed minus 25x. Now after straight calculations, one gets x cubed minus 23 divided by 12 all squared, x squared plus another terms equals to 0. Now let me remind you here that if one develops x minus a times x minus b times x minus c, one gets x cubed minus a plus b plus c x squared plus other terms. This means that the sum of the roots of our polynomial here, a plus b plus c, is actually equal to 23 divided by 12 all squared. Because our tangent line passes through D twice, this means that the point minus 4 here is a double root of our polynomial. This actually yields that minus 4 plus c is equal to 23 divided by 12 all squared. And after a straight calculation, one gets that the third root of our polynomial is c equals to 41 divided by 12 all squared. Oh, actually I should have denoted this x. And if we plug this third root into the equation of the line, one gets y equals 62,279 divided by 1,728. Now let me write these down again properly. We have x equals to 41 divided by 12 all squared, and y is equal to 62,279 divided by 1,728. Now because everything is positive, this is actually equal to the square root of x minus 5 times x plus 5. So it is power 1/2, which is equal to a minus b times c times a plus b all divided by 8. This is actually also equals to a squared minus b squared all times c divided by 8. Now because x is equal to c divided by 2 all squared, one gets that c is equal to 41 divided by 6. Now if you plug the value of c here and do the math, one easily gets that a squared minus b squared is equal to 1519 divided by 36. Moreover, and by the Pythagorean Theorem, one knows that a squared plus b squared is equal to c squared, which is equal to 41 divided by 6 all squared. Solving both of these equations for positive rationals, one gets a, b, c equals to 20 divided by 3 halves, and 41 divided by 6. We can actually easily check that this is a right triangle, and moreover, if you compute its area, one gets 20 divided by 3 times 3 divided by 2 all divided by 2, which is actually equal here to 10 divided by 2, which is 5. Bingo! We are done here, but notice that we can find infinitely many rational triangles verifying this by applying Diophant's code method infinitely many times. Now we move on to investigate another famous cubic equation, namely the Bachelor equation y cubed equals to x squared plus 2. One can easily see that 3 cubed is equal to 5 squared plus 2, which is also equal to minus 5 squared plus 2, and this means that the couples plus or minus 5, 3 are both solutions to our equation. Diophantus of Alexandria had knowledge of these solutions almost 2,000 years ago. And after reading this in his book, Pierre de Fermat claimed that plus or minus 5, 3 are the only solutions to our famous equation. This was a turning point in number theory when things got between the hands of Euler, the absolute genius. In the next section, we will follow the incredible proof of Euler that plus or minus 5, 3 are the only solutions to our cubic equation. But before we do so, let us get back to the Pythagorean equation a squared plus b squared equals c squared. I'm gonna show you here something you have never seen before to find all the Pythagorean triples. Therefore, fasten your seatbelts because this is gonna be a very dangerous ride. Indeed, one can factorize a squared plus b squared in the set of complex numbers to get the equivalent equation c squared equals to a minus ib times a plus ib, where I refers here to the imaginary number I squared equals minus 1. One can actually consider the numbers of the form a plus ib, where a and b are both integers, as integers themselves. A new kind of integers, of course, essentially because the sum, the difference, and the product of any two of them is a number of this form that satisfies quite the same algebraic rules as integers. Euler went even further and assumed that these numbers might as well verify unique prime factorization. Let me remind you that this implies if x and y are both integers with no common divisors except 1, such that their product is a perfect square, then this implies that x and y are both perfect squares, or equivalently that x is a square of a certain number u and y is another square of a certain number v. Let us now get back to our main problem and assume that the integers a and b share no common divisor except 1. Then one can imagine that in our new world of numbers of this form, that a plus ib and a minus ib share no common divisors except 1. The equation c squared equals a minus ib times a plus ib says then that this product is a perfect square in our new world. In particular, this means that a plus ib and a minus ib are both squares of numbers of this form. For instance, one can write a plus ib equals to a certain u plus iv all squared. After development, one finds that this is equal to u squared minus v squared plus I times 2uv. Let me write this latter equation down again. One gets that a plus ib equals to u plus iv all squared, which is actually equal to u squared minus v squared plus I times 2uv. So if we take these squares of the modules in these equalities, one gets that the module of a plus ib all squared is equal to the module of u plus iv all squared, which is also equal to the module of u squared minus v squared plus I times u v times 2 all squared. This yields that c squared, which is equal to a squared plus b squared, is equal to u squared plus v squared all squared, which is also equal to u squared minus v squared all squared plus 2uv all squared. Surprise! This is the formula that generates all the Pythagorean triples. Now one good question is, how come did we derive our formula so easily? I won't answer this question here, and let me get back to our main problem, which is to study the equation y cubed equals x squared plus 2, and to prove that the only integer solutions to this are plus or minus 5, 3. To do so, we will mimic the above proof here following Euler's idea. Indeed, one can factorize this in the following fashion. It is actually equal to x plus square root of minus 2 times x minus square root of minus 2. Euler did not care about the meaning of square root of minus 2, and he treated this as any other number. Now one might as well imagine that both of these numbers share no common divisor except 1, in which case both of them are cubes of a certain number of the form a plus b square root of minus 2, where a and b are integers. For instance, one gets that x plus square root of minus 2 is equal to a plus b square root of minus 2 all cubed. Now a simple computation gives a cubed minus 6ab squared plus 3a squared b minus 2b cubed all times square root of minus 2. It follows by computing real and imaginary parts that x is equal a cubed minus 6ab squared and that 1 is equal to 3a squared b minus 2b cubed, which is also equal to b times 3a squared minus 2b squared. This latter implies that b is a divisor of 1, in which case b is equal to plus or minus 1. Actually, b cannot be equal to minus 1, because in this case 1 is equal to minus 3a squared minus 2, which is impossible because 3a squared minus 2 is always positive unless a is equal to 0, in which case 3a squared minus 2 is equal to minus 2, which is different from minus 1. Therefore, b is equal to 1, which yields that 1 is equal to 3a squared minus 2, in which case a squared is equal to 1 and a is equal to plus or minus 1. Now if you plug this here, one gets for a equals 1 cubed minus 6 times 1 times another 1, which is equal to minus 5. In this case, one gets y cubed equals to x squared plus 2, and after a small computation, this is equal to 27, so we get that y is equal to 3. Now if a is equal to minus 1, one gets the second solution, x equals 5 and y equals 3. Bingo! Let me go through this again. Actually, we proved that if x and y are both integer solutions to y cubed equals x squared plus 2, then they must be equal to plus or minus 5, 3. Fantastic! This ends our trip into the realm of cubic curves, and we will investigate those in depth in future lectures. Thank you for listening.